A parity bit, or check bit, is a bit added to the end of a string of binary code that indicates whether the number of bits in the string with the value 1 is even or odd. Parity bits are used as the simplest form of error detecting code. There are two variants of parity bits, even parity bit and odd parity bit. In the case of even parity, the number of bits whose value is 1 in a given set are counted. If that total is odd, the parity bit value is set to 1, making the total count of ones in the set an even number. If the count of ones in a given set of bits is already even, the parity bit's value remains 0. In the case of odd parity, the situation is reversed. Instead, if the sum of bits with a value of 1 is odd, the parity bit's value is set to 0. And if the sum of bits with a value of 1 is even, the parity bit value is set to 1, making the total count of ones in the set an odd number. Even parity is a special case of a cyclic redundancy check, where the 1-bit CRC is generated by the polynomial x plus 1. If the parity bit is present but not used, it may be referred to as mark parity or space parity. Parity, in mathematics, parity refers to the evenness or oddness of an integer, which for a binary number is determined only by the least significant bit. In telecommunications and computing, parity refers to the evenness or oddness of the number of bits with value 1 within a given set of bits, and is thus determined by the value of all the bits. It can be calculated via an XOR sum of the bits, yielding 0 for even parity and 1 for odd parity. This property of being dependent upon all the bits and changing value if any one bit changes allows for its use in error detection schemes. Error detection: if an odd number of bits are transmitted incorrectly, the parity bit will be incorrect, thus indicating that a parity error occurred in the transmission. The parity bit is only suitable for detecting errors. It cannot correct any errors, as there is no way to determine which particular bit is corrupted. The data must be discarded entirely, and retransmitted from scratch. On a noisy transmission medium, successful transmission can therefore take a long time, or even never occur. However, parity has the advantage that it uses only a single bit and requires only a number of XOR gates to generate. See Hamming code for an example of an error-correcting code. Parity bit checking is used occasionally for transmitting ASCII characters, which have 7 bits, leaving the 8th bit as a parity bit. For example, the parity bit can be computed as follows, assuming we are sending simple 4-bit values 1001. This mechanism enables the detection of single-bit errors, because if one bit gets flipped due to line noise, there will be an incorrect number of ones in the received data. In the two examples above, B's calculated parity value matches the parity bit in its received value, indicating there are no single-bit errors. Consider the following example with a transmission error in the second bit using XOR. There is a limitation to parity schemes. A parity bit is only guaranteed to detect an odd number of bit errors. If an even number of bits of errors, the parity bit records the correct number of ones, even though the data is corrupt. Consider the same example as before with an even number of corrupted bits. B observes even parity, as expected, thereby failing to catch the 2-bit errors. Usage: because of its simplicity, parity is used in many hardware applications where an operation can be repeated in case of difficulty, or where simply detecting the error is helpful. For example, the SCSI and PCI buses use parity to detect transmission errors, and many microprocessor instruction caches include parity protection. Because the I-cache data is just a copy of main memory, it can be disregarded and refetched if it is found to be corrupted. In serial data transmission, a common format is 7 data bit, an even parity bit, and 1 or 2 stop bits. This format neatly accommodates all the 7-bit ASCII characters in a convenient 8-bit byte. Other formats are possible. 8 bits of data plus a parity bit can convey all 8-bit byte values. In serial communication contexts, parity is usually generated and checked by interface hardware and, on reception, the result made available to the CPU via a status bit in a hardware register in the interface hardware. Recovery from the error is usually done by retransmitting the data, the details of which are usually handled by software. RAID, Parity data is used by some RAID levels to achieve redundancy. If a drive in the array fails, remaining data on the other drives can be combined with the parity data to reconstruct the missing data. For example, suppose two drives in a 3-drive RAID 5 array contained the following data: drive 1, 01101101, drive 2, 11010100. To calculate parity data for the two drives, an XOR is performed on their data: AAAA01101101, XOR 11010100, AAAA 10111001. The resulting parity data, 10111001, is then stored on drive 3. Should any of the three drives fail, the contents of the failed drive can be reconstructed on a replacement drive by subjecting the data from the remaining drives to the same XOR operation. If drive 2 were to fail, its data could be rebuilt using the XOR results of the contents of the two remaining drives, drive 1 and drive 3, drive 1, 01101101, drive 3, 10111001, as follows: AAAA 10111001, XOR 01101101, AAAA 11010100. The result of that XOR calculation yields drive 2's contents. 11010100 is then stored on drive 2, fully repairing the array. This same XOR concept applies similarly to larger arrays, using any number of disks. In the case of a RAID 3 array of 12 drives, 11 drives participate in the XOR calculation shown above and yield a value that is then stored on the dedicated parity drive. History: a parity track was present on the first magnetic tape data storage in 1951. Parity in this form, applied across multiple parallel signals, is known as a transverse redundancy check. This can be combined with parity computed over multiple bits sent on a single signal, a longitudinal redundancy check. In a parallel bus, there is one longitudinal redundancy check bit per parallel signal. Parity was also used on at least some paper tape data entry systems. On the systems sold by British company ICL, the 1-inch wide paper tape had 8 whole positions running across it, with the 8th being for parity. 7 positions were used for the data, for example, 7-bit ASCII. The 8th position had a hole punched in it depending on the number of data holes punched. For a contrary view, Seymour Cray, premier designer of supercomputers, held parity designs in contempt. He felt it showed poor design. If you designed your transmission paths to be reliable, you would not have to waste resources on parity. His famous quote on this was, "Parity is for farmers." After he later included parity bits on the CDC 7600, Cray reputedly said that, "I learned that a lot of farmers buy computers." See also, BIP8, parity function, references. External links, different methods of generating the parity bit, among other bit operations.